wait another couple of moments because a few people are entering.
Mark, I am ready.
Okay, maybe we should start then. Well, I'd like to repeat the welcome from the previous session to people from all around the world. It's 10 a.m. in Chernivtsi, and whatever your local time is, wherever you should be. My name is Mark Dennis. I'm at the University of Birmingham in the UK. This is a very special meeting to me. This is the Correlation Optics 99, the very first international scientific meeting I ever attended, and it has always been interesting to see the arc of the subject over the last, well, I guess 30 plus years that the conference has been running, quite how much these ideas, which were seen perhaps not always as critical, are now very much have an international attention all around the world. And we also, those of us who've been to Chernivtsi in person, who are international, have always enjoyed the hospitality, generosity, and welcoming nature of our Ukrainian friends and colleagues. And I join my other colleagues in wishing that we can have the next one of these meetings in person back in Chernivtsi. The first speaker in this morning's session is our conference chair, Oleg Angelsky, who wants to talk, give an introduction to the Correlation Optics Conference.
Dear colleague, the title of my report, Introduction to Correlation Optics Conference, the title of report from singular correlation optics approach to the prospects for the effective use of structured light. Based on the achievements of intensive research in the areas of correlation and singular optics over the past 50 years, confident progress in the study of structured light is increasingly clearly and powerfully visible. This is clearly evidenced by a number of thematic articles in leading physical journals and reviews published over the past from 5 to 10 years. Generally speaking, the term structured light, also called customized light, or individualized light, or sculpted light, or shaped light, refers to light fields that are shaped so that to have specific spatial or temporal patterns and degrees of freedom, such as intensity, phase, polarization or photon spin, frequency or wavelength, time, and coherence. Unlike a standard laser beam, which has uniform plane wave or Gaussian distribution of light intensity, structured light can be manipulated to exhibit various complex shapes in the spatial or temporal domain. With the rapid development of laser source optical beam shaping, technologies, spatial degrees of freedom, control has also made significant progress, leading to development of new classes of optical beams. As a result, various spatially structured light fields were proposed and experimentally realized, including Airy beams, Bessel beams, Weber beams, Matthew beams, Innes-Gauss beams, caustic beams, Gauss beams, and Hermite-Gauss beams. These beams have unique optical properties such as a lack of diffraction, self-healing, and the ability to carry orbital nodal momentum, which are associated with their specific spatial intensity distribution and phase structures within their two-dimensional transverse spatial profile, which allows precise control over the dynamics of light evolution. By taking into account the polarization characteristics of light, it is possible to accurately form spatially different complex distributions to change the spin properties of the photon. Two prominent examples of broad interest are optical vortexes carrying optical angular momentums and cylindrical vector beams. In addition, the spatial coherence of light, a second-order statistical optical parameter, provides additional depths of difference that can be used to shape light. By controlling these spatial depths of fields, the beam's properties can be further refined, allowing for more precise manipulation in a variety application ranging from optical imaging, microscopy, microparticle capture, optical computing, optical communication, and laser processing to quantum information, leading to practical application with economic impact. Meanwhile, advances in ultrafast laser and pulse shaping technique have made it possible to generate optical pulses with virtually arbitrary shapes in their one-dimensional time profile. Pulse shaping of light, especially in the ultrafast region, such as pulse amplification, optical frequency cones, and pulse state generation, has already proven its value in wide range of applications. These advances continue to push the boundaries of light manipulation for scientific and technological innovation. The joint shaping of light in the three-dimensional spatio-temporal domains by accessing its temporal and spatial depths of field is called spatio-temporal structure wave packets. Research into spatio-temporal wave packets has made significant progress in recent years due to advances in the temporal shaping of the spatial structure of light. Traditionally, spatio-temporal packets are viewed as spatially temporally separable entities, where their spatial and temporal components are treated independently in the spatial domain, with notable examples including extended modes of focused wave, X waves, zero waves, Airy Bessel wave packets, and other forms, all of which resist both diffraction and dispersion effect simultaneously. In recent experimental demonstration, after 2017, spatial temporal packets were synthesized with specific correlation between different degrees of freedom. Using these new methods, temporal frequencies can be entangled with their corresponding spatial wave vectors, allowing the generation of diverse localized spatial-temporal structures such as space-time optical vortexes, space-time light sheet wave packets, space-time spiral wave packets, and toroidal pulses. These new spatial-temporal wave packets exhibit unique physical properties such as transverse on orbital angular momentum, diffraction-free propagation, tunable groove velocity, and time-varying optical properties due to existence of spatial temporal couplings, where spatial and temporal effects becomes entangled. This results in different behavior during propagation, focusing the interaction with matter, opening up new possibilities for light control in modern application. Here we present, here during our conference, here will be presented the comprehensive review of recent advances in spatial temporal structured wave packets, covering fundamental concepts, their generation and processing methods, characterization techniques, as well as their application challenge and future opportunities. Now I would like to show you the schematic illustration of recent advances in spatial temporal structure wave packets from, for example, fundamental, generation, characterization, application, and prospecting. In general, I would like to expect that among the report that will be presented at our conference, we will see examples of the implementation of ideas that advance this new promising direction in development of modern optical science and photonics. Thank you very much for your attention. I hope we will find all answers on the questions concerning the new direction of investigation in the structure of light. Thank you again.
Thank you very much, Oleg. I think if we have a couple of moments. I don't know if anybody would like to ask a question to Oleg on his very well broad presentation of the subject.
I hope that all answers on my reports we will find during all reports during our conferences.
I'm sure we'll see. We see many of these concepts that you've introduced over the next few days. So if nobody has any other questions, let me bring us to the first of the invited talks, which is Greg Gbur, who I see has joined us. So Greg, I don't know if you can share your screen with us.
Yes, I will do so. Let me see if I can get it going. Can you hear me okay?
Yes, that's fine. So, well, I will hand over to Greg, who can introduce his talk himself.
Okay, thank you very much. It's great to be participating in this conference again. And like everyone, I wish I could be there in person. Partly, I think my concern is my own country these days and the risks of coming in and out of my country. But nevertheless, I'm happy to be here and see so many friends and colleagues, and look forward to hearing more from everybody. So today I was going to talk about deterministic singularities and partially coherent vortex beams, which has been sort of a mild obsession of mine for a few years. And I'll give a little bit of an introduction to this and some background, because of course, and some of this Professor Angelsky already covered about talking about advantages of structured light. For me, I focus a lot on free space optical communication. We know that light propagating in atmospheric turbulence suffers from distortions that can adversely affect applications. We know that partially coherent beams are resistant to atmospheric turbulence to some extent, that they can have lower intensity fluctuations. And we also know that vortex structures can be used to encode and multiplex information and are, in a sense, resistant to atmospheric distortions themselves. And the thing that I've always been interested in is, can we mix these partially coherent and vortex properties together to improve communications? And the problem is that a vortex is a deterministic phase structure, usually in a monochromatic field, where partially coherent implies a randomized phase, which I often say that the two do not play well together. And the result of this is that even if you try and impose a phase vortex on a partially coherent beam, you'll find that on propagation it decomposes into vortices of the correlation function, which are less than ideal for applications. So, however, though, over the past 20 years, in fact, people have pointed out a number of different ways in which you can get a so-called deterministic vortex in a partially coherent field and have that evolve somewhere along the propagation path. And when I mean a deterministic vortex, I mean a vortex associated with a zero of intensity. And so it doesn't matter if you're measuring a correlation function where your observation point is, that zero of intensity of your beam is always in the same place, and there's always going to be the same phase twist around it, regardless of how you measure it, which is what we really want if we want to look at using vortices for applications. And so a list of things that I'll kind of run through. The oldest class are separable phase or circular coherence beams, beams that always have a deterministic vortex on propagation in free space. Then I'll talk about beams that evolve a deterministic vortex in the far zone, which I started calling Rankine vortex beams. And then we can have, based on that, we can talk about beams that evolve a deterministic vortex at a designed distance that, for lack of a better name, I just called deterministic vortex beams at the time. And those are relatively new, that I introduced in about 2023. And the two really new ones that I'll mention are beams that periodically revive a deterministic vortex that I call deterministic vortex revivals, and beams that start with a deterministic vortex and end with a deterministic vortex in the far zone. And I'll call those elliptical basis beams. And I usually don't like to give just an overall outline, but here I like to point out the sort of completeness of this list, that kind of every scenario is covered. Them always being there, them being there far away, them being there at the beginning and the end of propagation, and pretty much every other situation you can imagine, though I'm sure there's more. Now, a little bit of an introduction again, though, for this crowd. I probably don't need to say too much about it. Phase vortices in coherent fields. We know that we have this 2 pi twist, that around a zero of intensity. That's sort of the typical thing. And we have Laguerre-Gauss beams, intensity, and phase on the right. And that topological charge, that 2 pi multiple of phase, that ramp that you get, that's what we call the topological charge. It's an integer value, and it has to be for monochromatic fields. And it's discrete, and it's also stable under perturbations, which is part of the reason why we like it for thoughts of communications and sensing. We can multiplex and demultiplex multiple vortex orders for increasing communication bandwidth. And all of that has allowed us to think about using vortex beams, and people have tested for optical communications. And as I said, we specifically call a phase vortex that circles a zero of intensity, we call that a deterministic vortex. It's kind of a singularity in a partially coherent field that's sort of pinned to a zero. And actually, I think the last time I was in Chernivtsi, which was over a decade ago, was the first time I sort of observed one of these sort of things and talked about seeing these sort of singularities pinned to zeros in partially coherent fields. So this is kind of bringing things around rather nicely. Now, of course, we'll be talking about partial coherence. I also probably don't need to say a lot about coherence theory to this group, but this is a slide I borrow from the ones I usually give to my grant program managers. So a little basic, but we'll give just the fundamentals that we need. Typically looking at relatively narrowband quasi-monochromatic fields. So the fluctuations that we're interested in are largely spatial fluctuations. So we're looking at partially coherent fields in space. We characterize them by the correlation function, the cross-spectral density, which is the product of U star at R1, U at R2. We have an ensemble average in this case, which is just a very convenient way for constructing unique cross-spectral densities. And I like to note, and this is a little different than traditional, that you can write the cross-spectral density in terms of a field correlation product. You could express it in terms of sort of a separable deterministic field, a U star of R1, U of R2, and then a correlation function that depends on R1 and R2. And it is to some extent an arbitrary separation, but it's a nice one for me because we like to stress there are some phase features that are not the result of random fluctuations, but are associated with propagation or some sort of manipulation we've done. And that's different from the way that the cross-spectral density is usually decomposed, where all the phase terms are lumped in the correlation, and then you write, instead of U, the square root of intensity. Now, to give a little background and history about all this, I think the first discussions of vortices and partial coherence came about around 2003, was when people started thinking about what are the general properties of vortices and partially coherent fields. And I was part of one of the groups that was looking at this. It was, as is a grand tradition in physics, there were multiple people who thought of kind of the same approach or the same idea all about the same time. So there are 2 or 3 papers I can point to really starting the thinking on this. But the logic that we'll talk about is just the way you can think about it is we already know that the cross-spectral density satisfies a Helmholtz equation in both variables. So del 1 is with derivatives with respect to R1, del 2 is derivatives with respect to R2, K is the freak omega over C. And so if you want to ask, when do we typically expect to see singularities in the cross-spectral density, we could say, well, if we fix R1 or R2, the cross-spectral density acts just like a monochromatic field. So we expect to see exactly the same sort of singularities in that situation that we would in a monochromatic case. And so those will be the typical singularities you see in the cross-spectral density. And tend to call those correlation vortices these days because they're vortices of the correlation function. But it's important to stress that they are vortices of the 2-point correlation function. So they aren't necessarily related to the intensity of the field at all, and they're going to depend on the choice of observation point. So if I'm looking at singularities in terms of R2, the position of those correlation singularities are going to depend on my choice of R1. And that's why we say these are not exactly ideal for applications, because vortices whose position sort of depends on an extra degree of freedom is a little not ideal for trying to analyze a vortex structure for applications. Now you might ask, can we see these sort of deterministic vortices in partially coherent fields? And the answer is not usually. And this was something we start by noting the way you can prove this is with Emil Wolff's coherent mode representation, where any partially coherent field can be written as a sum, finite or infinite, of a product of these so-called coherent modes. So it's an incoherent superposition. The phi-n's are orthonormal, the lambdas are positive or non-negative, and n is a total number non-zero modes. And you can find the intensity by setting R1 equal to R2. So it's just this sum. And then the reasoning about the existence or non-existence of these modes is pretty straightforward, because you could say, okay, when would we expect to see a zero of intensity? We look in the transverse XY planes, we've got 2 degrees of freedom. From the structure of the sum, in order to get a complete zero of intensity, we have to have the phi n be equal to 0 for each mode in exactly the same location. So if you think about it in terms of systems of equations, that means you have to satisfy 2n equations with 2 degrees of freedom. And the only time that that's going to be a typical solution is if n is equal to 1, if you've got the fully coherent case. If n is equal to 2, you've got basically 4 equations and 2 unknowns. So it becomes very unlikely. So from the traditional way of thinking about singular optics, we can say only in the fully coherent case do we expect zeros of intensity to be generic. So that was a little not promising. So quite for a while, we focused on just the correlation singularities. But then you can ask, under what special cases can you get zeros of intensity and a deterministic vortex associated with it? Well, first of all, let me note that you're not going to get it if you're looking at sort of a traditional partially coherent vortex beam. So the classic example is you make a Gaussian shell model beam, and you do that by, say, taking a Gaussian beam, you focus it through a rotating ground glass plate, and that gives you a random phase structure. You then collimate it again, which gives you a Gaussian shell model beam. So you have the Gaussian intensity envelope, the shell model correlation, and then you put it through a spiral phase plate and you impose a vortex on it. So at least immediately you've imposed a vortex structure on it. But if you look at what happens on propagation, you'll find that that imposed structure disappears quite rapidly. So in the source plane, just we force this phase structure on it, even though it's got a non-zero intensity. And that phase structure does cause the intensity to get very low when on propagation in the center. You get a donut-like mode, but you find you get these correlation singularities. And these are examples for 2 different choices of a fixed observation point. And you find the singularities end up in really completely different locations depending on where our fixed point is. So Gaussian shell model vortex beam possesses no deterministic vortex structure. But people already had noted, and I give credit to Sergei Ponomarenko and Mart Susskind and collaborators back in the early 2000s for recognizing that you can make a beam with a deterministic vortex that sticks in place. And one way you can do that is with the coherent mode representation. Again, you say, okay, let the phi NMs be Laguerre-Gauss modes with the same azimuthal order, but different radial orders. Now they're still all orthogonal, but they have the same exact spiral phase twist. And so the combined beam is always going to have that deterministic vortex on axis on propagation. And Sergei, I think, first introduced an analytic closed form class of such beams in 2001, and in 2003, he and collaborators showed experimentally that works. You can also have a similar class of circular coherence beams introduced by Santer Sierra and collaborators in 2017. And there, you basically construct an ensemble of beams with different focal lengths. So V in this case is just a variable that represents a focal length. This lambda essentially represents a probability distribution for different values of the focal length. The size become your vortex beam of whatever order you want. In 2017, the original authors just considered a Gaussian case, but you can just as easily convert it to a vortex case. And the vortex will remain propagation invariant again because it only had the only azimuthal structure of that field is that vortex. And in just this year recently, my students and I published a paper. We tried to analyze all the free space characteristics of these sort of circular coherence vortex beams. Some colleagues in Finland earlier, unbeknownst to me, had kind of looked at similar things, looked at such beams in turbulence. But you do find that, yeah, you maintain the vortex on propagation. You do end up with a non-trivial structure, like the intensity of the beam does odd things on propagation, including self-focusing. And one interesting thing is to say, question to ask is, can we just set up a situation where we get a really pure deterministic vortex at a specified distance? And before I answer that question, let me note that I've also been looking at some of these beam classes in turbulence. In 2024. We looked at the OAM spectrum of different types of partially coherent beams with orbital angular momentum, and noted that there are certain propagation distances where some classes work better than others. If you look at the circular coherent vortex beams, you find that their standard deviation stays low over shorter propagation distances, and that standard deviation is the standard deviation of the OAM spectrum, and then shoots up. A coherent beam tends to do terribly altogether. If you look at a what I'll call Rankine vortex beam or a twisted Gaussian shell model beam, they have a higher standard deviation at shorter distances, but a lower one at longer distances. And this is sort of frustratingly typical of what happens in atmospheric propagation studies, where you find the answer to the question, does my beam work better than other beams in turbulence? The answer ends up being, it depends. So it still remains sort of an open question of how to optimize these sort of problems. But let me get to some of the other really neat classes of beams we can consider. And to give a little history, because I love to talk about the origins of projects and how they came about. Since 2004, I've been using a beam wander model to construct partially coherent vortex beams. At the time, back in 2004, the most natural way to construct a partially coherent vortex beam, that beam that it definitely had a vortex in it, was to say, let's imagine we've got a vortex beam U, and we assume that its center axis is a random function of position. And then we can construct the correlation function as an ensemble average over this center point R naught. Like I said, I've been using this for years, and in 2020, with Professor Zhang and Tsai, we started looking at a broader class of these beam wander beams than I'd considered before. And in particular, one thing that we did is we decided to look at propagation effects in detail, which I'd never really looked at how well these things do on propagation. And Professor Zhang actually did the calculations, and he came back to me and he said, well, this is weird because in the source plane, you end up with a very non-deterministic vortex structure. You end up with, even if it's a vortex of order 1, you end up with pairs of equal and opposite vortices whose positions depend on the observation point. He said, but as you propagate it, suddenly it looks very much like a fully coherent vortex beam. You get that really pure phase value, and the lower row is just the zeros of the real and imaginary part, just to clearly show the zero. And I almost had a panic attack here because this seemed very much contrary to what I understood vortex beams to do. Considering, for instance, the Gaussian shell model case I mentioned previously, where the vortex gets less prominent and more random on propagation, here the opposite was happening. And so I panicked a little bit, but thought about it a little more and realized that the answer is that this beam wander class of beams that I later started calling Rankine vortex beams based on the fact that they have a Rankine vortex OAM structure. Well, that beam wander beam is just the Fourier transform of the ordinary Gaussian shell model vortex beam. And I already had recognized this back in 2009, that if you look at a shell model beam, it's got essentially a deterministic vortex in the, say, U0, and then it's got a correlation function that depends only on the difference in positions. That correlation function can be Fourier decomposed, and if you put these two equations together, you get that the cross-spectral density represents just a bunch of vortex beams with different tilts, that they're just a bunch of them incoherently superimposed with different tilts. But if you Fourier transform a tilt, like you put a tilted beam through a lens, that tilt becomes a shift. So the Rankine beam, the shell model beam, which is a bunch of tilts, becomes a bunch of shifts when you Fourier transform it, which is the beam wander beam. So in essence, what we were seeing here is the natural evolution of the shifted beam, the beam wander beam, evolving into a Gaussian shell model beam where a vortex is always on the central axis. And of course, that comes about because as you propagate to the far zone, you're doing a Fourier transform. And then we started thinking about, okay, well, what happens if we use a fractional Fourier transform? We know that a fractional Fourier transform roughly mimics what happens in diffraction theory. So we said, let's use a source which is a fractional, let's use a source that's a fractional Fourier transform of some fundamental vortex state or a Gaussian shell model state. And if we use that kind of that pre-treatment of a fractional Fourier transform, then on propagation, that fractional part will get undone, and we should get a deterministic Gaussian shell model type vortex at some propagation distance. And so this is a lot of the math of it. We say, all right, we're going to consider, we introduce a fractional Fourier field. We can combine that fractional part and that propagation part together into a single operator. And you can ask at what propagation distance does the propagation and the fractional part cancel? And you find that that's at the z distance k sigma squared tangent of alpha, where alpha is a fractional parameter, k is the wave number, sigma is the Gaussian width. And I note that it's independent of the actual state of coherence. We can do this regardless of the coherent state of the beam. And sure enough, doing simulation results, you find that if we design it to be a deterministic vortex at 100 meters, you'll find that sure enough, at 100 meters, you get a perfect on-axis vortex associated with intensity. If you go certain distance, propagation distance on either side away from it, you eventually find that you get the kind of characteristic second vortex coming in from infinity and kind of ruining the purity of the mode. And this can be done for, in principle, any propagation distance. So for 1,000 meters, you also find that you can tailor your beam where you just get that perfect isolated vortex right on the central axis exactly at 1,000 meters. Now, the one caveat to this about coherence is one important thing does happen if you start with low spatial coherence. And that is, well, two things actually. One is there's a self-focusing effect that becomes prominent. Because of our fractional Fourier stuff, you end up finding that your beam has a little bit of self-focusing and tends to maximize its focusing in your designed range. But also, the depth of field, as we call it in this case, the range over which the vortex appears effectively deterministic, gets a lot smaller as you decrease the spatial coherence. So in this case, we used a really low spatial coherence. The two outer pictures are sort of the limits of what we argued could be remotely considered a pure deterministic vortex. And now here it's only 0.2 meter or 0.4 overall range of propagation over which you could say you have a deterministic vortex. So there are limitations, but we're currently looking at, hey, can we use these things in atmospheric turbulence? Would they give any improvement because they include vortices and partial coherence? Now, the next thing is, and this was just me really free associating at some point and saying, what other ways can we make a deterministic vortex appear on axis? And then you could say, well, we could try and make them appear periodically. And here we turn to Bessel beams. And apparently we can really get very close to a deterministic vortex in this case. So we start with a Bessel vortex beam. And first we start with a 0th order one. And we actually include two of them with slightly different propagation constants. And the reason we choose slightly different propagation constants is there will be some propagation distance at which these two will be perfectly out of phase and cancel each other out. And you can figure out that this combination will periodically have a 0 right on axis when z satisfies this equation, and where n can be any integer. So it's a periodically repeating 0 on axis. Now, you can take, though, if you want to make this partially coherent, you could say, let me take an incoherent superposition of this with a Bessel vortex beam. And so we add to that an incoherent mth order vortex. And then at the special z values, the thinking is the coherent part of beam will vanish at the origin. And then at the origin, you'll just be left with your vortex, which will then be pretty much on axis. And at least superficially, that seems to be exactly what happens. Here's a range. We designed it to repeat after 100 meters. And so simulating it, you can see at 0, you've got the on-axis vortex. At 100, you've got the on-axis vortex. Halfway in between it, somewhere around 50 meters, though, you actually see that you get this non-deterministic vortex again. There's no vortex on axis. You get the pair again, that characteristic pair whose position depends on the observation point. That's kind of what's shown down here, that at z equals 0, that vortex doesn't care. It stays at the origin, even when you change the observation point, but the other singularities at other distances move around. So yeah, you can actually make these singularities revive. However, then there's a little caveat to this, which we realized after we did this for a while and just shows that I got a little carried away. If you actually say what happens to the field close to the origin, so when your Z2, say, is very close to the origin and R1 is fixed, well, you don't get something that actually is a pure vortex structure at the origin, because you've got a Z2 star here, and you've got a Z2 to the M here. And so what you're really getting is not actually a rigorously deterministic vortex. You're getting a vortex that's approximately deterministic because this first term actually goes very close to 0. You get an approximate null field region at those special distances, which allows the second term to dominate and for things to look very largely coherent. And you can show that this is the case just by modifying our original field. If we introduce an amplitude A to our weird Bessel combination and then ramp up the magnitude of that A, you can find, for instance, that in the first case, we've got m equals 1 vortex. In the second two, you've got m equals 2. In the first row, I let that amplitude go up to 5. And you can see that that doesn't really wreck things. You still get a very centralized vortex. But if you let A go up to 15, well, now we're back to a non-deterministic case. We get multiple singularities in the region. It's no longer a pure singularity associated with some sort of zero. So this example is a little cheating. I'm pretty sure there's a way to modify it to make it actually exact, but for the moment, this sufficed. Now, the last one I like to mention is an elliptical basis beam. And this came about, we said that, okay, a Gaussian shell model beam starts with a deterministic vortex and ends with correlation vortices. The Rankine vortex beam starts with a random correlation vortex and ends with a deterministic vortex in the far zone. And then I wanted to ask, is it possible to make a beam that starts with a deterministic vortex and ends with a deterministic vortex, say in the far zone? And the trick here was to use elliptical Laguerre-Gauss beams. These beams, if you look in the source plane, if you're choosing a higher order, mth order vortex, it has an elliptical intensity pattern, but still has a ramped up spiral phase structure. But the nice thing is, because it's basically a Laguerre-Gauss type beam, when you go to the far zone and you propagate this to the far zone, it's again going to be an elliptical Laguerre-Gauss beam. It's just going to be rotated 90 degrees, because that's what Fourier transforms tend to do to Gaussian type structures. They just rotate them. And so that means, suppose we construct an incoherent beam by taking a bunch of elliptical beams, all with different orientations. Because every orientation in the source plane has a zero on axis, the combined beam will have that same zero on axis. And then the same thing will happen in the far zone. They'll all just be, every member of the ensemble will just be rotated 90 degrees. So when we add them all up together again, they'll all have that zero on axis again, and we'll get our deterministic vortex recreated. But in intermediate distances, you'll have a mess because these beams end up with a very complicated structure in intermediate propagation distances. And these beams were originally introduced in 2006. All right, there we go. So we construct our basis with this ensemble of rotated beams. And then we ask what happens. Let me make sure I don't run over my time and speed through a little bit. In the source plane, if we look at an LG02 case, this is the cross-spectral density phase for a bunch of different observation point positions. So if the observation point's over here, it's that plot and so forth. And you can see, yeah, the phase structure rotates around, but you always end up with that singularity on axis. In the intermediate region, somewhere around like 700, 800 meters, your singularities are fully non-deterministic. They really depend entirely on where you're at. If you propagate to the far zone, if you go really far away, probably impractically far, but very far away, you can find that your singularities have again sort of converged into the middle, and you have this nice deterministic vortex again. Now, the one caveat here, this didn't actually work at first. When we first tried this, it didn't seem to work. It seemed like it was non-deterministic even in the far zone. And I realized that this was because you still get this spherical wave factor, this very rapid oscillating phase factor in the far zone. And every member of the ensemble has a different spherical wave phase factor because they've all got different spherical waves depending on their orientation. And that screws everything up. So you have to imagine collimating your beam at the output, and then so another Fourier, well, not really a Fourier transform, but just removing that quadratic phase factor, and then you get a nice vortex structure again. If you do the LG01 case, it turns out by symmetry that the vortex is always there no matter what, which kind of makes sense when you think about it. So, in summary, we typically expect to see partially coherent vortex fields lose their vortex structure on propagation, their deterministic structure. We can construct this really nice family of beams where this is not the case, and where you can have vortices manifest in different propagation regions. And my plans for the future, which are kind of ongoing, is kind of to simulate all of them through turbulence to see if any of these different approaches gives you a more robust vortex structure than a traditional just monochromatic coherent vortex beam. And I'll stop there in case there's any questions. Thank you very much.
Thank you, Greg. Do we have any other questions? Any questions for Greg in the last few minutes before? You can either post a question in the group chat, or you can put your hand up and ask a question.
And you're always welcome to yell at me later if you like.
Obviously, it's quite difficult under these Zoom circumstances. Please go ahead if you.
May I ask you, Igor Mokhun?
Yes.
All your reasoning, what can you say about the all your reasoning fulfillment for any kind of turbulence?
Oh, are we working on this for any type of turbulence, or so the particular type that the particular stuff that I'm interested in is sort of clear air Kolmogorov turbulence. Now, we definitely know that if it gets too strong, things are going to fail entirely. So a lot of the goal is to see whether we can increase the robustness to stretch out the propagation range over which we can maintain a stable singularity. Though in principle, it's a method that should be kind of turbulence agnostic as long as it's not so strongly scattering medium. Hopefully the same advantages would apply.
Thank you.
Yes. I think there was another hand raise or question.
Hello, Mikhail Gorsky, Chernivtsi National University. As far as I understood, in practical application, it is important to know the revival distance of a deterministic vortex. How can this distance be predicted or calculated?
Yes. So for instance, if you look at the ones based on fractional Fourier transforms, the really nice thing is that at least in free space, you can do all the math analytically. You can figure out exactly the distance where it'll happen. So you can design your source to match that. You can also get a very good estimate of the depth of field analytically. Now, the catch is, at least from initial calculations done in turbulence, that changes things because it turns out that the optimal distance where you see the best vortex gets pushed closer to the source. That we're still working on. So the best we can do right now is say we know exactly where it will be in free space based on the parameters given, but in turbulence, the optimal case is still to be determined.
Thank you.
You're very welcome.
Maybe we should move on to the next speaker, if that's okay. So, thank you very much to Greg.
Thank you.
next speaker here? If so, please share your screen. Only want your PowerPoint presentation.
Hello?
Hi.
Hello? Can you see my slide?
Cannot see it now.
Can you just adjust?
You need to
Huh?
share your screen again. You need to share your screen again.
Can you see my slide?
Green button, please push.
Huh? What
Push.
did you push?
Push green
Push
button.
what? Pin button?
Demonstrate
Share.
screen. Share
Where is the
screen.
pin button here? Okay, pin button. Which button?
The center of the bottom, at the bottom.
Ah, pin, okay. Yeah.
Share.
But
Share.
can you
Screen.
see my slide?
You need to share screen.
This is my slide. How can I load my slide here?
On the
It's not.
as he said, there is a green button at the bottom of the Zoom window with an
Just
arrow.
a green button?
Green button, share screen.
Where is the green button?
And after that, choose your presentation.
Green button here?
Zoom window. Should be an option in Zoom to share screen.
Yeah, I can see everything, but I don't understand here. Oh,
I don't know, Mark, if you want to share your screen for a second and show them the Zoom window as you can see it to point out the button.
Yeah, it will be in English.
which button you talk about here? I cannot see any button here.
You had the share screen on before you left the room. There is a share. You need to. We cannot see your presentation in Zoom. You need to switch it on in Zoom.
Yeah, but I did it.
Yeah, but we cannot see it now. You do it again.
Yeah, so you can see me, all right? But I cannot load my just view graph here. How?
So Greg suggests I move to show you my screen. So if I show you my screen, I'll just share for a moment.
So he said,
I'll just show you my screen.
hello? Hello? Hi, what should I do? Huh? Shit.
So
Hello?
I send one picture to the chat.
Where is the green button?
Message.
Yeah, I cannot see.
You can have a look there.
Where is the button window? Just I cannot see any green button. International, I can see here. International conference, I did it, but I cannot see green button. No. Zoom button. Just a second. What? Yeah, I have it now on screen. Yeah, but I cannot see green button here. What is green button? I cannot see green.
Your screen.
Yeah, in Zoom, yes,
your
I
Zoom
can just,
window, you press.
I can hear just voice,
S.
but I cannot see any just green button here.
You press Alt plus S, the keyboard.
No, this is only Zoom I can see, but Zoom, I'm in the Zoom. Huh? Huh? What? F? Plus F. Plus F. I should do plus F? No. What happened here? Oh, God.
Your keyboard, you press Alt plus S.
Alt.
S and S.
F.
S.
Huh?
Alt S.
Alt. F.
S.
A.
S means sun. S.
S. Alt S. Okay. I did Alt S, but nothing.
If you have options on your computer at the top for Zoom, there should be some sort of option for window where you can share.
I can see only my face here, video, audio, and the background, statistics, information. So this is called my just video mirroring, something like only that kind of stuff here.
Need some
So
sort of
video is now in just the transmitting, video is receiving. So that's all I can see here.
I wonder whether we should, because it seems with difficulty. I think if we have the next speaker, maybe we should switch around the speakers.
Okay, that will be better. Yeah, I will do next. Okay, yeah, just start just another second. Yeah, okay.
Yeah, so,
sorry about it. Yeah,
I'm sorry. Is Konstantin Bliokh here?
Yes,
Okay.
I'm here. Can you hear me?
Yes. Are you okay to give your talk?
Yeah,
first?
absolutely. Let me try to share my screen. I don't know if it works. Let me try. Keynote. So.
Hello? 야, 이씨, 아니네. 뭐가 이래, 개 같은 게.
Something is wrong with my sharing as well. Okay, let me try once again. Okay. Does it work?
Yeah. Yes. Thank you, Konstantin.
Okay, no worries. So then I will start with my talk, and I'm glad to see everybody here, and it's great that this conference continues to happen, and hopefully next time we will meet in person. So I would like to talk about our recent works about, of course, various topological structures in waves of different nature, from nano-optics to ocean waves. And basically, most of the results here are from our two recent papers. The first one published in a new journal called Newton, and I can highly recommend this new journal for publication of your results. And second one was published in Nature in collaboration with Fudan University in China. The first work was done in collaboration with big team in San Sebastian. Okay, and I will start with the introduction, which is probably not needed in this audience. So, of course, the basic or most important part, the type of topological forms in waves are phase singularities or vortices, which were introduced by John Nye and Michael Berry 51 years ago. So last year we celebrated 50 years anniversary of this discovery. So if we consider a scalar wave function for simplicity on the plane in two-dimensional space xy, and we can plot the intensity and phase of this wave function, which can have some space varying intensity and phase, we can typically see a picture like this. There are points where intensity vanishes and the phase is ill-defined in such points, called phase singularities. If we go around such points, the phase grows by plus minus 2 pi in the generic case. And in the third plot, I plot simultaneously phase and amplitude via brightness and colors. It's a nice representation of the wave function. Okay, so the increment of the phase around phase singularity, modulo 2 pi, is called topological charge. Now, if we consider such a single vortex, in the circular symmetric case, the wave function can be written like this. So it grows proportionally to the r and has the standard phase factor e to the il phi. And it's easy to see that this wave function is an eigenmode of the orbital angular momentum operator known from quantum mechanics. And the topological charge L is at the same time is orbital angular momentum quantum number. So it's a very nice correspondence between topological and dynamical property of the same wave function. Okay, we can construct higher order vortices. For example, in two-dimensional space, these are given by such Bessel-type solutions provided by interference of plane waves propagating in all directions with different phases. And then the wave function has a Bessel function, radial Bessel function, and the same vortex phase factor. And what is important is that the size of, for example, the first maximum of this Bessel function is controlled by the wavelengths. So for the vortex of charge 1, the typical size of the intensity distribution is the wavelength, diameter of this bright ring. And you cannot shrink this vortex to really sub-wavelength scales. Okay, and the higher topological charge, the larger is the size of this ring. Okay, and as we know, this is a very generic phenomena. So vortices or phase singularities can be found in any linear waves, and probably the earliest example is the phase singularities in ocean tidal waves. Here I show a modern map of tidal waves in the world ocean, and again, by brightness is the amplitude of the tide, and colors denote the phase of the tide during the day. And you can see many dark points with all colors surrounding them, which are called amphidromic points in oceanography. And again, generically, they have topological charges ±1. And for example, if we take this amphidromic point in the center of Pacific Ocean, and we compare with our simplest Bessel-like solution in two-dimensional wave equation, we can see that correspondence is quite good. And the wavelengths in this case is of the order of 10,000 kilometers. Okay, and a similar Bessel-type solution can be realized in any two-dimensional waves, for example, in surface plasmon polaritones, as it is done in this 2006 experiment. These are plasmonic vortices with topological charges of 1, 3, and 5. Okay, and recently we came up with an idea that phase vortices, that is 2 pi phase increment around some area, can appear not only around zeros of the wave function, but also around poles. So, for example, if I consider this model complex function of x and y, it has 2 zeros, phase singularities, and has 2 poles. And we can see that the phase goes to pi around poles as well. And of course, such solution with amplitude singularities cannot be realized in homogeneous space because we cannot have infinite amplitude of the wave function. But if we have a not simply connected space with excluded areas, which we call holes, then such solution can be realized. So, for example, if I consider on the left is the usual vortex with 0 amplitude in the center, and on the right there is a solution of wave equation with suitable boundary condition in a plane with excluded central area, with excluded circle. And then it's easy to see that there is a solution which, instead of going to 0 at the origin, each diverges at the origin, behaves as 1 over r, and has the same phase factor. More specifically, if the first type of the vortex can be provided by the radial Bessel function of the first type, the second type vortex around the hole can be provided by the Bessel function of the second type, which diverges in the center. And what is important, that now the size of this type 2 vortex, as we call it, is determined only by the size of the hole. It's not related to the wavelengths anymore. And if the hole is much, much smaller than the wavelengths, no problem. The vortex solution can be present, and it's always localized on the edge of this hole. Okay, so this is a way to create very sub-wavelength vortices. For instance, here it's lambda over 20 scale. And remarkably, we found such type 2 vortices on the same map of ocean tidal waves around islands of New Zealand and Madagascar. So you can see the phases go to pi around these islands, and the amplitude of the type is very high on the coast of these islands. And moreover, the typical size of such vortices is λ/6 in terms of the tidal wavelengths. So it's really sub-wavelength vortices. Okay, next we suggested a simple model how such vortices can be generated and described. And it's a very simple wave function given by the interference of a plane wave propagating horizontally and a point dipole, which generates the maximal field along the orthogonal y-axis. And interference of the plane wave and dipole generates such vortices. Again, dipole has an amplitude singularity because it diverges at r equals 0. So we need to exclude some area around the origin. So we can see around this area, the phase goes to pi, and the intensity is very bright because of this 1/r divergence of the field. So the total topological charge of this field is 0 because we have opposite vortices of type 1 and type 2 with opposite topological charges. Because far away from the dipole, the field is just a plane wave. But the total angular momentum of this field is not 0 because the bright type 2 vortex contributes much more to the angular momentum than the dark type 1 vortex. So the total angular momentum and the existence of these vortices can be controlled by the phase between the plane wave and the dipole. Okay, and if we compare this model wave function with ocean tidal maps around New Zealand and Madagascar, we see that correspondence is quite good. We only adjust two parameters: relative amplitude of the dipole and relative phase of the dipole. That's it. So with two parameter adjustment, we can more or less explain this phenomenon. And possible physical explanation of why this model can be relevant is that the big islands like New Zealand and Madagascar, they also oscillate under the moon gravity, and they oscillate with the same frequency. So we really they can act as a dipole source of ocean tidal waves. So we really have an interference of propagating tidal wave and oscillating dipole of the island. Okay, now coming back to optics, we can excite such type 2 vortices around real holes in two-dimensional wave systems, such as plasmon polariton. So, for example, if we have a hole in the plasmonic surface, we can illuminate it from the top with a circular polarized light. And due to the spin to orbital angular momentum conversion, it excites a vortex of charge 1, determined by the circular polarization of the incident light in the Z component of the surface field. And such experiments have been known, for example, these two papers in 2010, 2019, but they were done for the holes of the wavelength order size. What we show here in a numerical simulation, that the size of the hole doesn't matter, actually. You can scale it down to any sub-wavelength size. For instance, here it's λ/50, something like this. And the solution is exactly scales with the size of the hole. So it can be deep sub-wavelength vortex. It's just not so easy to observe it on this scale. But mathematically, there is no limit. So we tried also with San Sebastian experimental teams to observe it experimentally using Fanon polariton surface waves. And we generated a periodic array of holes, sub-wavelength holes. And there was a side propagating plane wave, like Bliokh plane wave in this polaritonic crystal. And the interference of dipoles excited at the holes and this propagating wave generated exactly type 2 vortices around such holes. So these are numerical simulations and experiments. The typical size is here λ/3, not so much, and lambda is for Fanon polariton wavelengths. So it's much less than the free space wavelengths. At least conceptually, this confirms our prediction. So you can see also on numerical simulation that type 1 vortices, phase singularities, are also present here in the dark field zones as usual. But what really determines the main distribution of the wave function is the type 2 vortex, because it has much higher intensity, and so it dominates in this field distribution. Okay, so finally I show how a real type-dependent field evolves around in such type 2 vortices. The first animation is the model of plane wave and point dipole interference. The second animation is the tidal waves around New Zealand from real data. And the third animation is also experimental data from Fanon polyretonic whole experiment. So you can see that these are very similar solution and really the same generic phenomenon. Okay. Now, in the second part of my talk, I would like to consider topological structures in vector waves. And first, let me remind you that the classical vector waves, like electromagnetic or other waves, are described by a complex vector field, F dependent on coordinates R. And this complex field can be parameterized by two real vectors A and B, which describe polarization ellipse traced by a time-dependent field. So A and B are the major and minor semi-axes of this ellipse. And generic singularities in such fields are the so-called C points of circular polarization, where the ellipse degenerate to a circle. This was first suggested by John Nye in 1983. And so here is just a random distribution of two-dimensional ellipses, and you can see C points of perfectly circular polarization. And if we plot a quadratic scalar wave field, f.f, you can see that these C points correspond to phase singularities in this scalar wave field. So topological indices of such C points are plus minus 1/2. Why? Because if we trace orientation of the polarization ellipse around the circular polarization point, it rotates by plus minus pi instead of pi. So the index is plus minus 1/2. And if we go into 3 dimensions, so now ellipses can be arbitrarily oriented in 3D, then Isaac Freund showed sometime before that the orientation of such ellipses generally forms a Möbius strip structure around the C point. And this was first observed in optics in this experiment, and then with Etienne Brasselet, Miguel Alonso, and Karen Wolke-Sepulveda, we observed it also in acoustics. Okay, and another type of topological structure in vector waves, which recently attracted some attention, is a skyrmion. So if we consider distribution of vectors of instantaneous vector field, they can have all directions in 3D. And in some area, we can map these directions onto the unit sphere. So if this mapping covers the whole sphere, we can calculate the topological winding number of this mapping, which is called topological skyrmion number. And it is also quantized, so generally can be +1 - 1. So this is example of skyrmion field structures. The term came from magnetism, and recently it was shown that classical wave fields also exhibit such structures. This was first shown by Guy-Bartal group from Technion, and then more papers came. Okay, and so the idea of our work, which I would like to present, is to show this all this topological structure of vector waves. They naturally appear in water waves. So we consider water surface waves like gravity waves or capillary waves, doesn't matter. And in deep water gravity waves, as a plane wave propagates, we know that water surface particles, they trace circles, which are shown in this picture. And these circles, they actually like circular polarizations in optics, just orientation is different. And if we interfere monochromatic several plane waves with the same frequency, water waves, then each point of the water surface traces its own ellipse generically, the same generic polarization ellipse as in optics. And now the field is the local displacement of water surface particle, R. It has all three components, X, Y, Z. And so we can measure these polarization ellipses, their properties, directions of displacement R, and so on. So this is a numerical simulation. If we interfere several plane waves on water surface with the same frequency, how each point of water surface moves in time. You can see they all trace ellipses, and these black dots, they correspond to C points, where ellipse degenerates into a circle. Okay, so we performed an experiment with Fudan University. In the first experiment, we considered three-wave interference. We interfered three plane waves propagating in three directions, as shown here in such a setup experimental. So the wavelength was about 2 to 4 centimeters. And to measure the wave field, we used very nice techniques called fast checkerboard demodulation. So you can see that the background of this water tank, it's a top view. The background has a checkerboard pattern. And imaging this pattern with a camera, we can see distortions of this pattern produced by elevation of the water surface, because each elevation acts as a lens. So then numerically, we can demodulate this distortion of the pattern into the Z component of the water surface wave field. So in this, on the right, you can see already measured Z component of the wave field. Let me see. Here it's time-dependent wave field in three-wave interference. And on the right with colors, it's a complex Z field. And you can see that it's exhibit a kind of hexagonal lattice, as it should be, with the alternating L +1, -1 vortices. Okay, this is measurement of the Z component of the field, but we also need X and Y displacement of the particle. Although we couldn't measure them directly, we can calculate them using equations of motion, because they are proportional to the X and Y gradients of the Z field. So we reconstructed the whole three-component vector field, X, Y, Z, and plotting instantaneous displacement of water surface particle, we found that in each cell of this hexagonal lattice, the displacement vectors are mapped onto the unit sphere, forming a skyrmion, and calculating topological charge from experimental data, we see that it's quite close to 1. Okay, and also, if we consider the points of vortices, the phase singularities in the Z field, they are not actually zeros of the whole 3D field, because they have X and Y component. And actually, these are C points, because in these vortices of Z, in these phase singularities of Z field, there is XY circular polarization of actual motion of water surface particles. And then measuring polarization ellipses around such points, we observed Mobius strips as it follows from the generic theory. So these are ellipses reconstructed from experimental measurements. And just to show how water particles move along this Mobius strip, this is the animation. You can see that everything moves continuously. There are no discontinuities. But if you trace the orientation of the ellipse along this circle, along this big circle, you can see a pi rotation, which corresponds to the Mobius strip. Okay, and finally, we also generated Bessel beam vortices in water waves. Surprisingly, that this hasn't been done before, because such experiment could be done many years ago. It's very easy. So we used 24 sources of water waves distributed along a circle, and just controlling their mutual phases, we generated Bessel vortices of charges L from 0 up to L = 8. as shown here. This is experimental measurement of the Z field. So, for example, this is a real-time evolution of the Z field. It's L equals 0, the maximum is in the center. L equal 1, there is one azimuthal maximum which rotates with the wave frequency, and L equal 2, two azimuthal maxima rotating. L equal 8 is 8 azimuthal maxima rotating with the same frequency. Okay, and here I would like to emphasize that these water wave vortices, these are not the usual wave vortices, because usual classical vortices in hydrodynamics, they are steady flows of the fluid with not zero circulation and vorticity. And this vorticity is not quantized, it's a real number. In contrast, what we observe is interference of linear waves. There is no real steady flow in this vortex. So vorticity vanishes in the linear regime. And what circulates is the phase of the oscillating wave function. So essentially, this is a quantum-like vortex in a classical fluid. Okay, and what is, again, we emphasize that this vortex is not scalar because the displacement of particle is three-dimensional. So if we write down all three components in such vortex, we can see that they are eigenmodes of the total angular momentum operator, including orbital and spin part. And spin part is a spin-1 operator, essentially the generator of SO3 rotations in space, the same as in electrodynamics. Okay. Here we plot canonical momentum density in such water surface vortices, which is essentially a phase gradient, and the circulation of this phase gradient provides orbital angular momentum, and also a Z component of spin angular momentum. Spin angular momentum is normal to the elliptical trajectory of the water surface particle. So we see that both orbital and spin degrees of freedom are present in such vortices. And here is the final part of my talk, perhaps the most interesting. We thought that since there is such a similarity between water wave vortices and generally structured water waves and electromagnetic waves, there should be similar dynamical effects. And we have energy density, we have momentum density, we have spin density. So we decided to place a probe particle in such water waves and see how, if there are like radiation forces and radiation torques on such a probe particle. And we expected to see something similar to optics. So if it's so, here is a scheme of a particle in a vortex field. There should be a so-called gradient force proportional to the gradient of intensity, and it's directed radially in the vortex field. There should be a radiation pressure force, which is proportional to the momentum density, which is phase gradient, and it should be directed azimuthally in such a vortex field. And there can be also a torque, Z component of the torque, proportional to the Z component of spin in such a field, or XY circularization this field. So we performed such experiment. We took small plastic particles, like 2 millimeter size, placed floating particle, they float on the water surface, placed, then switched on the field, the interference field. And first we found that for L equals 0 field, which has maximum intensity in the center, the particle was attracted to the maximum intensity zone and trapped there. So it's essentially the same as Ashkin's optical trapping, but now in water waves. Yeah, I can show you the animation. So please ignore this checkerboard pattern. There is a very pale particle in the center. You can see that it's stably trapped in the center of such a zero-order Bessel mode. Okay, in the second experiment, we generated L equal 2 vortex mode, and the particle was trapped in the bright ring of the second Bessel function of the second order vortex. And at the same time, we observed orbital motion of this particle produced by the radiation pressure force produced by the orbital angular momentum of such vortex. Here is the movie. The particle is attracted to the maximum intensity ring, and it goes around this ring, as you can see here. So it works very well. Okay, and finally we took larger particle and higher charge vortex, L equal 8, and the larger particle is the ping pong ball. So the size is 4 centimeters. And we observe not only orbital motion of this ping pong ball, but also its spinning motion around its axis. And the direction of the spinning motion precisely corresponds to the spin density in the area where this ball is trapped. So you can see the movie. So it's all three effects. Ping pong is radially trapped. It's azimuthally moving due to the orbital angular momentum, and also it spins around its own axis due to the spin angular momentum. So essentially, this is an exact analog of optical experiments made more than 20 years ago. Here shown this parallel 2003 paper with small particles and optical Bessel beams showing radial trapping, azimuthal orbital rotation, and spinning due to the circular polarization. The only difference that in optics you can control the sign of circular polarization independently of the orbital angular momentum. But for water waves as well as for acoustic waves, the sign of spin, local spin density, is determined by the sign of the orbital angular momentum. There is no independent spin degree of freedom. Okay, so to conclude, I have shown our recent result on so-called type 2 subwavelength vortices, which can appear around holes in two-dimensional planes. And such vortices can be localized to arbitrary subwavelength size. And then I showed generation of water wave vortices, skyrmions and Möbius strips in gravity water wave experiments. And finally, I presented that such waves can be used for manipulation of floating particles exactly as optical or acoustic manipulations. Thank you very much for your attention. I don't know if I did it on time.
Yes, that was great. Thank you, Kostya. We got plenty of time for discussions. Would anybody like to ask Kostya anything? Yes, please.
Thank you, Kostya, for the impressive talk. And my question is regarding this type 2 vortices. So what are the limits of the sizes for the holes to be applicable to hold this interaction between like play wave and dipole?
Well, as I said, mathematically, there is no limit. You can scale down to as much as you wish. But physically, I believe that the smaller the hole, for example, in metallic surface, it's more difficult to control the experiment. First, it's more difficult to excite vortex because the coupling is smaller. If you excite it with a incident wave, right, the coupling to the hole, which is, for example, lambda over 100, is very small. Second, it's very difficult to observe, to measure this field, because you need really, I don't know, electron microscope or something like this, really a very, very sub-wavelength accuracy measurement. But with usual near field techniques, you can go, for example, to, I would say, up to lambda over 10.
Thank you.
I think Igor Mokin has a question as well.
Okay, thank you. Kostya, if we have the optical situation, for example, optical tweezers, the conventional flows in the liquid, for example, may completely destroy the capturing. Have we similar effects which may destroy your capturing in water?
Oh, absolutely, yes. Of course, different kinds of flows, steady flows in fluids can be a problem for such experiment. But in our experiment in simple water tanks, when we excited interfering waves, everything was worked quite well because it's a closed tank. We had absorbent boundaries, so we didn't observe any like serious perturbation. But for example, if you can try to apply it to open sea situation, some waterways in the ocean, then of course some flows and streams can distort this picture.
Okay, thank you. And the second question, as to the vortices of the second type, we have in the denominator the R in the second degree. Can we use the R in other degree, for example, for
Well, in the basic type of such vortex, which is charge 1, it's 1 over R. So it's R in the first degree. It's 1 over R. But for you can construct higher order solutions, but this higher order solution can be more confined to the edge of this hole. So it will be maybe more difficult to observe, but mathematically they are present. But again, similar to type 1 vortices, to the usual vortices, these are not generic solution if you just consider some random interference. So you need to provide some special conditions to excite such solutions.
Thank you.
Do we have any other questions or comments? We do have some time. Well, if not, maybe we should move on then. Thank you to Kostya again.
Thank you.
Do we have Young Song, the last speaker, ready to resolve the technical issues with the screen? Is Jung Son here to try to give the talk again from the previous slot? If not, maybe we should move on again, and hopefully he'll be able to join to give it at the next talk. So do we have Yoko Miyamoto here? Yoko,
Hello.
are you okay to give your talk now?
So is it okay? I was given a different Zoom link for my presentation. Is it okay to go ahead with this?
I think it's okay to go ahead with your presentation now.
Okay, so give me a moment, please.
Okay, thank you.
Okay, can I start? Okay, Thank you. So thank you for the opportunity to give this talk. It's been 4 years since I last gave a talk at this conference. I was hoping maybe this year it was going to be in Deterministic, but unfortunately the situation did not allow. So my talk this time is scattering and change in non-separability of light. So I am from the University of Electrocommunications in Japan. This is the short, brief slide about my group. This current work was supported by this project on modeling for scattering process and scattered field. So we have 3 women who are PIs, and to give an example of some work that I am not going to present today. So this is work on 3D imaging through a highly heterogeneous double composite random medium. So if you are interested in this type of work, you can later contact me. So outline for my talk today is non-separability between space and polarization in polarization state. And then I will talk how this relates to our polarization speckle. And then for the work that we've been doing towards quantitative analysis on this phenomena, and then summary and outlook. So first, about some general things about non-separability between space and polarization state. So non-separability, as I think many of you already know, is a classical analog to quantum entanglement, and it differs from two entangled particles in the sense that space and polarization state cannot be basically divided between different parties. So that means no spooky communications at a distance. Then, but they do have the same mathematical structures, so tools developed to analyze entanglement can be applied to the analysis of non-separability. So this is a slide illustrating what I mean by this non-separability. So first we look at the situation with homogeneous polarization, where space and polarization state are mutually independent. So we have the double slit interference experiment here. So the light is coming in, they are going through 2 slits, and at the end we have interference fringes. And from these interference fringes, we can infer, for example, the distance between these 2 slits. So some information on pre-propagation distribution can be inferred. Now we think about putting a halfway plate in one of the slits, and so this would be creating an inhomogeneous polarization. So space and polarization state are somehow correlated, but phase relationship is being maintained between the light at the 2 slits. At the propagation end, we no longer see the interference fringes, but we see the polarization gradient. And if we ignore the polarization information, then there is no structure here that is equivalent to the interference fringes. So we cannot infer the distance between the 2 slits anymore. We can also ignore spatial information. That means that results in our losing information about the polarization. So although this light at the output is locally fully polarized, if we ignore the spatial information and look at this all in one go, we see that we have unpolarized light when we average in space. So we lose polarization information in this way. So this is what we mean by non-separability, that we ignore one information, we lose the other also. So some of the mathematical tools from quantum entanglement has been used to characterize this situation. And today I'm going to focus on concurrence, which have been shown to be linked to the global degree of polarization. So by global degree of polarization, I mean the degree of polarization that we get when we ignore the spatial information. So if the light is unpolarized when spatially averaged, then concurrence becomes 1. We have a highly non-separable light. Of course, we do not know that there can be light that is unpolarized locally, and here that is not what we mean. So this concurrence actually applies for the pure states for looking at non-separability. So for what we mean by pure states here is that light where local degree of polarization equals 1. So this difference in degree of polarization when we go from local to global is actually the sign of the non-separability. So similar information can be gleaned from our examination of spatial correlation for polarization states. So here we have the Stokes parameters S1, S2, and S3, and we can look at the spatial correlation between these 3 Stokes parameters, where the angular brackets are being used to denote spatial averaging. So if we look at this correlation function at delta R equals 0, then of course this is just the measure of the localized degree of polarization. And if we look at this at very large distances where there no longer is expected to be any correlation, then this would be basically the spatially averaged Stokes parameters square of modulus. So if we have non-separable light, this first one, CP0, is expected to be close to S0 squared, and CP infinity should go to 0. So the gap between the two indicates the non-separability. So how can separability change? Operations that do not change separability are operations where polarization-independent lossless spatial transformations occur, such as propagation through isotropic media or spatial phase modulation, etc. Another type of operation that do not change separability is space-independent lossless polarization transformations. So inserting wave plates for the entire field to pass through. Operations that change separability is space-dependent operation polarization state, or polarization-dependent operation of spatial distribution. We will see examples of both later on. And then this change in separability can also work both ways. You can go from separable to non-separable, or non-separable to separable. So in the example with the double slit experiment, inserting this halfway plate here is creating the non-separability. This is of course space-dependent polarization manipulation. So we can have space-dependent operation on polarization state. This will change our separability, and quantification of separability change. So here I am talking about just two slits. But if we make many more slits and insert wavelengths, different wave plates on all of them, then this can gradually become something like a model of a scatterer. And the quantification of this separability change can be a new way to characterize scatterers. And as I said, we can go from separable to non-separable, or non-separable to separable. So these are the basic questions that I have been pursuing. Can scatterers be classified into those that change or do not change separability? Can scatterers be characterized by how much they change separability? So I would like to first have a look at what we have done in the past with polarization speckle. These are my collaborators. So Rakesh Kumar Singh and Gangi Reddy Sara, both from India. And these are the types of experiments that we have done. So what we have here is to look at change in non-separability during scattering. What we would like to do is to have an input beam with variable separability. And in this case, we have used ground glass, which is a weak scatterer and should not change separability very much. So usually the assumption with the ground glass is that they do not change polarization very much. So there should be not very much of this position-dependent change in polarization. So basically the non-separability at the input should mostly equal non-separability at the output. So to have beams that have variable separability, one technique we have used is we change the overlap between two orthogonally polarized beams that are otherwise copies of each other. And the other technique is that we have two orthogonally polarized beams. We would just add rotating phase on one of them. And so by changing the relative amplitude between the two, we go from separable to non-separable and then again to separable. And then these beams are scattered, and we looked at what happens to the polarizations distribution spatially. So the top one is an example of a separable beam that has been scattered. So we do see some structures here and there, but mostly mostly the state of polarization has not changed, and we have mostly mostly homogeneously polarized scattered speckle fields, and degree of polarization is high everywhere. When we start with a non-separable beam, we do have lots of structures in all three of the Stokes parameters, but again, the degree of polarization remains high everywhere. So to look at a little more detail, I'll start with the relative amplitude case. So this is a very simple experiment to do. So we have the light coming in from a laser. We have spatial light modulator that changes the phase distribution of just one of the two orthogonally polarized components. And a quarter wave plate to change the basis from horizontal vertical to right and left circular components, the ground glass plate to do the scattering, and then some polarization analysis at the output. So these are how the input beams are looking like. So as we change the direction of the half-wave plate, so half-wave plate is at this input. So this is changing the ratio between the horizontal and vertical components, and where, so at the output, in this case, we have just the left circular components. So this is homogeneously polarized. At the other end, we have very nearly mostly right circularly polarized beam. And in between, we have this non-separable beam with various states of polarization depending on where you are. And when you scatter these types of beams, for the homogeneously polarized beams, the scattered beams are also nearly homogeneously polarized, but in between we have this polarization speckle where state of polarization seems to be changing randomly over space. So this is the picture that I previously showed. We look at this by changing the imprinted rotating phase to have different topological charge. As we go to higher M, the structures are getting smaller, but otherwise they look relatively the same. And these are the correlation functions for the various Stokes parameters. And if we look at this as a function of the topological charge for the S0s, so this is just the intensity correlation, and the intensity correlation length is staying mostly the same. But this, what we call the polarization correlation, the correlation length is actually going down. So this is corresponding to the smaller, structure in the polarization speckle that we have been observing. So very different thing happening when you are looking at just the intensity versus when you are actually examining the states of polarization. Okay. For the control by overlap case, so this is where we have the incoming beam and we have the polarizing beam splitter. So one state of polarization is going in the anti-clockwise direction in this interferometer. And because this is slightly misaligned, the state of polarization that go anti-clockwise and clockwise come out at slightly different positions, and this is controlling the overlap. And then we have the ground glass as the scatterer, and we look at the polarization speckle. So here, the mostly overlapped case is homogeneously polarized. This is the separable case. Then as we go gradually to the no overlap case, the two orthogonally polarized components are experiencing completely different parts of the ground glass. And then as we do this, although at distance 0, the correlation in polarization is remaining high. So this is showing that the light is actually locally fully polarized, but at very large distances, we go from this highly correlated to basically 0 correlation. So this is showing that when we average over space, as I discussed before, state of polarization is no longer correlated. So this is showing us that we are going from non-separable to separable, from separable to non-separable case. So this is all very well, but we have not really compared the input and output polarization states. So to do this comparison in a quantitative manner, we have done some improvements in how we analyze. So again, I'm showing an experimental setup. So this is the case for the amplitude control case. So we have the laser coming in. We have polarized and half-wave plate to control the relative amplitude between the two components. We have spatial light modulator to modulate the phase distribution of just one polarization component. And first, we are looking at the beam that is being generated. So this is the state of polarization of this beam. So we are starting this light that is mostly vertically polarized, and then we are gradually going into mostly horizontally polarized light. And in between, we have modified the phase distribution for one of the components to give basically a vortex beam. So the combined beams have now inhomogeneous polarization as shown in this, mainly in this central part of this picture. And then we try to measure the concurrence of the beams, and we have experienced some problems, especially on both ends where the concurrence is is coming down. There's also some discrepancies between two modes of measurement at the center, but the lower concurrence parts are more problematic. So to think how this is happening, we look at how the Stokes parameters are being defined and measured. So S0 is the total intensity, but here we are averaging over space, so we are talking in terms of power. So this is S0 total power. S1, S2, S3 are the difference between power in the various combination of orthogonal polarizations. And these formulae can basically be used to estimate the Stokes parameters from the measured power. But what to do about S0? Because estimate of S0 is actually highly influencing the estimation of degree of polarization and thus the concurrence. So we measure these 6 different powers. So what should we do about S0? So that is one issue. Another issue is for low concurrence situations, we can have instances where the degree of polarization, because of experimental uncertainties, can actually go above 1, and that is also a problem in estimating the concurrence. To look at this problem, we look at how Stokes parameters should behave as a whole. So we look at this. This is what people usually call the coherence matrices. This is the unnormalized version, and we can also normalize this via S0, and it can be written in terms of the normalized Stokes parameters as in the equation 2. So the Stokes parameters as a whole should be part of this matrix, and an important aspect of this matrix is that it should be non-negative. So the usual technique that is being illustrated in this slide does not actually ensure that the matrix is positive, and this is basically causing many issues. So we take some hint from what people have done in quantum optics, as this rho is what is usually called the density matrix, and of course determining density matrices from experiment is what people call quantum tomography, and there are many discussions on this issue. So we have opted to use a model that looks like this, because this ensures that the density matrix is going to be non-negative, and we optimize these 4 parameters from the measured powers. So a little bit more of the details. So if we have the density matrix and we have the Jones vectors for whatever polarization states that we want to look at, then this equation 5 should give us the power for that polarization component. This is basically why rho needs to be non-negative. for optimization, we need an estimate of S0, so we average over all the combinations of the polarization components to have an estimate of S0, and use that to minimize this equation 7 to give us the parameters T1 through T4. And once we do this, we have this nice graph where the concurrence goes to 0 where they should be. And so we are now able to go on to the scattering experiment. So we have the scatterer here, and again another analysis of the state of polarization here. So this is how the scattered field is looking like. There is actually some issue with the camera, as I have discussed. So for the estimate of the Stokes parameters, we have opted to use the power meter technique. And by doing this, we have this input versus output concurrence pictures, and for the different types of ground glass. And we have a slope that is close to 1, but a little bit below, and we have an offset, which means that if you start with an input of 0 concurrence and do the scattering with the ground glass, you have a small increase in the non-separability. So, summary and outlook. So separability, non-separability is a characteristic of the optical field that may or may not be conserved during scattering. We have improved the Stokes parameter analysis, which has allowed us to estimate low concurrence values more or less stably. And using that, we have seen that input-output relation for non-separability was separability for ground glass scatterer with non-negligible position-dependent change in polarization observed. So outlook is that we think we should be able to estimate unnormalized Stokes parameters directly. That is, we do not need to have a separate estimate for the S0, which I think would be better, and then use that to characterize some scatterers, and maybe think about how this provides insight into how much spatial information is lost when change in polarization is not tracked. So thank you for your attention.
Thank you very much. Do we have any questions? Or yes, please.
Hello, Mikhail Gorsky, Chernivtsi National University. Really short question. First of all, thank you for nice presentation. And short question, you told that you had some problems with camera. And I'm curious, did you estimate how those, let's say, technical issues or whatever they can influence accuracy of measurement?
Okay. So this Stokes camera is by a Japanese manufacturer. I think what happened is they meant it for different wavelengths, but we asked one for the helium neon laser wavelengths, and they tried to patch it up, but maybe their job was not perfect. So we think that there is some issue with the algorithm that they use to, so they have something that acts like a wave plate in their camera, and they look at the readings from various pixels to calculate the Stokes parameters. And I think the algorithm they are using is a little bit off. So they tend to so the mapping from the what we think are the actual Stokes parameters to their output is somewhat nonlinear. Maybe we in the future maybe we can look at working with them to improve their algorithm. But for the moment, we find that the parameters are giving us more accurate results.
Thank you.
Any other questions? Maybe I can ask a question. Do you envisage some way of being able to combine this classical entanglement, non-separability, and concurrence together with any sort of quantum measurements? Because obviously, you know, at some level, it's all just measures of wave properties, whether we're talking about photons or not. Is there? Can you see some way that would be able to use these techniques for sort of measuring a unified entanglement between classical and quantum entanglement?
Okay, so I think some people have looked at hyperentanglement, where you have these types of non-separable spatial modes coupled with the photon pairs that are produced, for example, by spontaneous parametric down conversion. So maybe these improved classical measurements can improve the analysis of this hyperentanglement and maybe the application as well.
Okay, thank you. Are there any other questions or comments for Yoko? If not, let's thank her again, and hopefully we have our final talk now for the session, which is Jung-Young Son, if the technical difficulties have been overcome.
Okay, thank you.
Mr. Dennis, now we will try a short interactive segment. We will present the slides and Mr. Son will speak and provide commentary. Okay?
Yeah, good. Can you hear me? Can you hear my voice?
Yes, all right.
Yes, it's okay.
Can you hear, right? Okay, can I start? It's okay? Can I start?
Start.
Okay, thank you. I'm sorry to just make you the delay, right? And the disturbing, this process. I'm sorry. So my today talk is a Carla Moires for security applications. So this just work was done, me and the Professor Tatiana Venkel of this the Chernihiv University. Okay, next. Next, can you do? Okay, so there is a many security features to guarantee product authenticity and anti-counterfeit, because so many valuables and the goods and the expensive goods requires this kind of security features to just protect themselves, right? So there is many different security features is developed. So that just among that security feature, there are many different security features, the physical, digital electronics, nano and the DNA features. This is used to just block, counterfeit, and authenticate products and documents and deter fraud. So among these features and the physical security features include optical variable devices. This they use mostly the special optical elementers. And there is another called the tempered evident labels, security ink, and the unique serial numbers. This is a barcode and the QR code. This can be used. So all these the features, the OVD, the optical variable devices, are mainly diffractive optic element, such as hologram, structural colors, and diffractive optics. So this OVD is mainly depend on they just display different images or colors that are dynamically shifting and varying with the viewing angle and the light condition changes. So by doing this way, this makes them difficult to replicate. So another guy doing counterfeiting and hurting that authenticity. So they are blocking by this way. So now my question is possible. I can make the security feature device similar to OVD with the Moires. So here OVD is mostly dipractical optical elements, and here I already told embossed hologram, structural colors. So these are structural colors found, butterflies, mother of pearls. I give just the example of a mother of pearls, and you can see if you change and you have a different being just the condition, you can see this part enhanced and this part is enhanced and this part is more enhanced, something like that, and the color change. Also, there is a butterfly. Butterfly, the pigmentation of color. Color is just skin colors, some kind of pigmentation also. And also, they use a special lattice structure of butterfly. So this kind of just grating structures. They are lattice one, and another lattice is vertically. So on the heaven, there are two just lattice structures. They are is a 90 degree, okay, is arranged. So this is some kind of gratings. So you can use grating, and just this is grating, and you put your eye, and you can see the different colors. So this is if you change your just eyes, you can see different colors. So this is just color is dynamically changing. So this is I just give the examples here, and this color, this butterfly, and the one side is just blue. The other side is a dark blue, and they just change colors and depend on your seeing, okay, your viewing directions. So this is mainly kind of just all holograms. And hologram also you see the different directions. You can see the color changes. And this is Korean money, and we have holograms. And there's some part they said the structural colors. They also added here, but I cannot find. They don't. But anyway, and you see the different and the money, and this is a 50,000 won, and you see that these changes and the patterns, and by seeing your just the being directions. This is the 10,000 won, and giving another, and just the changing holograms they are installed here. So most of this lattice actually the size is just nano size. Okay, so nano size. And this hologram, actually this height is, the embossed hologram, the most about 400 nanometers they have. So this embossed, then the height is just, embossed height is 100, just 400 nanometers, but and the period is about 1 micron. So this period is slightly bigger than this is just structural colors. That's like a butterfly here. And this mother of pearls. Okay, next. Yeah. So now my question: how to generate, how to just make some kind of just characteristic of this the OVDs with the color Moires. So before that, let's talk about some kind of Moire forming principles first. So Moires, and you see there is a two regular plate, one and the bottom one and the top another, just regular, the pattern plate, and they are all transparent and they are overlapping on the top of just each. Okay, so this is and one, and this bottom one, and this is okay top one, and top one is the just the period is just slightly less than this bottom one. Okay, if there you do, and by overlappings, and that make and dense just sparse, dense, sparse, something like that, this kind of patterns. But when you change the thickness of this, each just on the top, okay, lines, and you can see that becomes more dense. And this you can have some kind of just Moires with just more dense, just colored, and Moires and you can generate. So next. So we talk about what is color Moires. And the color Moires, so typical and the Moires and classically, we talk about two regular patterns. They are black and white mostly. But now I'm talking about the color Moire making, just the way. And you see the Moire is just simply overlapping two just regular patterns. So if you just the overlap some kind of regular pattern on this is the monitor panels and or this kind of RGB color patterns, okay, arrange just the array of RGB color patterns, you can and make the colored Moires. So this is okay, this is you cannot see the colored Moires, but anyway, and I'll show you next. And if you slightly just thicker and the line, okay, you can have, you see the overlapping different color. This is only single colors, but this is overlapping the whole color, right? Changes. So by this way, you can change just the color. You can make a color Moires. Okay, next. Next. Can you do next? Yeah. So this is okay, the just the color patterns on there, and you have two different thickness lines. Okay. So one is this one is another one, and you just overlapping here, and this is make shorter. And if you make this kind of lines, you can see, and these two it make different the color Moires. They make color Moires here, so you can see that way. And this just the principle. Okay, next. Next. Yeah. So this is a typical pixel, just monitors, okay, pixel structures. So this is not, this is we considered most, okay, this is a typical one, but actually many just different, the monitors have a different pixels there. This is some kind of arrow stack. And this is a different, another one, and this is also arrow. So they are pixel shape is slightly different, and they have each just pixel, they have gaps. And this gap is very small, but in any case, they have just some of them is very large gaps here. Okay, next. Yeah. So when you just the inside our just monitors, the changing color principle is this is okay RGB, and if you this one, and all this, so if you divide each RGB colors 8 different segment, okay, so no just blockings at all, and this give white, and you give black to red, and here, so this is a typical already, and if you block 1/3 and here 1/3, just the red 1/3, blue 1/3, and the green just blue 1/3, the green 1/3, and this one slightly darker, and this is not white, this become gray. And if you have differently, and one block, another just completely black, one is just just small blocks, and if you make that way, and this color changes, color become darker, and this is a blue bolt, and you can make all different colors by this ways. And this is if you just make, and this is just just 3/8 you cover and just cover the just one the dark lines, and this is just half, and this is just 5, just 5/8 if you cover it, and you can make this cafe ore, cafe ore. So this is a coffee, okay, colors you can make this way. So this is the principle of making colors in this your just monitors. Okay, next. Yeah, this is another just the principle I talk. If you change the color composition here and the blocking is different, just amount, you can make whole different colors here. Yeah. Okay, next. So you can also make the slant way, and you see this kind of just well, also the slanted colors, color Moires you can also make. Okay, next. Yeah, next. Yeah. So if you see the Moire characteristics, and the Moire working as just some kind of beta frequency principles. So this delta 1 is some kind of first one, and the bottom one, and this is the top one. And this just subtraction, and gave this is actually original, just Moire, this is the period. So, well, and if a top plate has no thickness, and the period of two plate patterns are fixed, in that case, and this Moire is stable all the time, the same, even you change your view direction or not. So you just to make that one, and somehow you can just change here, and the top plate have no thickness, and and the bottom just plate with the thickness or not, it doesn't matter, but top plate should have a thickness. So to make just the Moire, and to make relative period of panel pixels changes as the viewer change her view distance or just the directions. So you can just make it on the next. Yeah, you can make this way. Okay, so this is a bottom plate. This is a display panel. On the top, you have this plate, top plate, having some kind of thickness. Well, of course, this must be transparent. So thickness T, it should have some thickness. Also, well, this plate, anyway, this color patterns, this is a line patterns is not important, but here you can have this kind of the relief structure, and if this is just the relief structure and the boundaries, this become just work as some kind of dark lines, and this work same as this way. So they have the same effect as this one, and so you can make to just make the Moire, the color Moire especially, is a change is just colors and well, and he's just some kind of visual effect. So you want to give, first you have to make, and the top plate have should certain just thickness. If you do that, you can make a color Moires changing. Okay, well, it's just colors, shifting colors, and you can make a dynamic just the visual effect. So this one is just the structures I'm talking. So this is actually RGB pixel structure here, and you put it here, some kind of writing device. So if you writing device, usually now this our monitors, and especially LCD monitors, you are just give a white light, but you don't need to give a white light. So you can give here just many different colors. So you can change, and or from here, you can also modify these colors through these filters, RGB filters, and in the right, just colors through these filters you can also change. So you can have the relief structure cases, and if you considering some kind of LCD panels, they have some kind of protection glass. So this is about 500 micron, and well here, and you have some kind of a relief structure, or you can have just a line structure with a slight just some kind of thickness. You can make it that way, and you can make Moires the shifting and the color shifting, and it gives some kind of a dynamic visual effect. Okay, next. So there is another method, so-called gap method. So you just make this first the top and the bottom one, and with certain gaps, air gaps. So this is air gap. So that means, so this is just right. You are seeing here, this is your visual device. It is eye or camera, if you put it this way. And but you see it here. And this has a different distances. And this side is becoming, and if you get in here, and this size is just longer distance. And this part, and it depends on this distance. And what change? They have just magnification change. And this one is a shorter distance. This is bigger, smaller. So by that bigger, smaller, you can have some kind of color effect. But this is actually not Moires, because so this is doesn't give and the dynamic effect, and some kind of just color shifting effect. Just you see only one directions and the same colors, like the color Moire appears all the time. Okay, next. So it's told, and you have to make it, and some kind of just display, and this is a RGB structure. You need to make this one some kind of just plate. The top plate have some kind of thickness, and with this one, and what happened here, and this bottom one, and going through, when you see it from here, and you are seeing this place, and but there's this one here, the one, this is reflected and appears at this spot, and this one reflected appears at this spot. So this is the original RGB and just the period, but this one is slightly becomes smaller. So by this way, if you this place, if you go further, and this becomes smaller than this one all the time, and smaller this side, and well, the difference becomes just less and less if you're going just these directions. So when your eye and seeing here, and if you see your eye, a human eye can just see the almost 100, just more than 100 degree in each eye, and the viewing angles it has. So you can use here the eye here, and you can see all these color changes here by just some kind of chirping effect, because the period of the color pixels become just here reduced, and here if you go increased. This is the same as just original. But anyway, if you go just away from your eye, and you can have just the color, just the period of color pixels become smaller. So by this, you can have some kind of this chirping color pixels. This chirped color pixels, you can have it. So this is what just make, and your Moire is actually shifting. Just if you change, because you change here, and you are seeing, and this shifting, you change here, this become here, and this is whole moving. So this gives us some kind of a shifting effect. Okay, yeah. Next. So this is some kind of just very easy just equations, and you need to just calculate this one. How much this just the period of this top. Okay, this the bottom plate is just the color period is changes. So this is by the calculations. This is very necessary. Only just needed to do, and if you can do, you can simulate what kind of just patterns will appear when you just put some kind of thickness there. Okay, so this is the one, and if you make, and the PPN is this is some kind of reflected, okay, just pixels just period, and this is the original period. If you make it, and well, this is the differences, and this become okay smaller all the time, right? Smaller than this one. So you just PP divided by PPN. So make it slight this kind of curve, and it also is because this is depend on just viewing distance. So when the viewing distance is 0.7 meters, and the viewing just the distance 1 meters, viewing this 2 meters, and you see how just this the period becoming smaller. You can see that way. So this is all the time less than just 1. Okay, so this is 1.003, 1.022. So this is slightly, and this just okay ratio is slightly bigger than 1 all the times. So why this one and the means, and this become smaller than this one. So by use these equations and this just curves, and you can predict. So what kind of and just color Moires appears when you just give okay just different and just line structures, and you can find it that way, and I'll show you next. Okay, give the next. So this is just experimental setups and the color Moires, and this is a display panel, and you put here some kind of thickness, having thickness, and the plate on the top is top just just the line patterns. This is should be color patterns. And you set your camera on this either here or center or this part and the left side. And this one, and use the here camera. You must use some kind of a wide angle, just objective you have to use. And if you do that, and you can record some kind of moving color Moires. Okay, next. Hello? Yeah, so this is black and white simulations. When I use top and bottom, they have a 1.27 and the 1.292 and the period. So this is just the millimeters, the period, and you can have here, this is a simulation, okay? So this is 1 meter, and you can have this one and the no t equals 0 cases. And this is a very regular patterns appears. And that's on this distance and about 0.81 meters. And this 1 meter cases, on these cases, there is about 10.85 and the period appears. But then you see that GV becomes 0.7 meters and 9.85 and 1 meters 10.01 and 10.1 and another is 10.4. So this is a period that becomes slightly changes. If you consider this is a 10.4, this is a 10, and this is a 4. So this is a 1, okay? This is a 1, and yeah. So you can have the 10 and just 1/10 of this one, yeah, this part. So you can have, so you can expect this kind of stuff. No, just a second. Okay, yeah, so this one, okay, 3.406 and the 3.3, you can see here, the one in the regular, with a t equals 0 cases, 9.4, just the number of the periods, and this is 10, and 0.7, 10, and the 9.8, 9.7. So they have become just opposite of these cases and these cases. Opposite, just the result coming out. Okay, next. Yeah, so this is theoretical simulations. If you do, anyway, so experiment, and you just put it here, the thickness, and this is 0 cases, you can have 10.9, 1.27 and 1.292 cases. Actually, you do experiment, and you have a very similar 9.9 and 0.7 cases, 10.2 and 10.4. Just lines coming out. So this just the experimental result is exactly almost the same, and the same as the simulation results. And the next, so this is 1.27, 1.292 cases, and these cases, well, I didn't say, but this 3.0, t equals 3.0 millimeters. And if you see here, the no t equals 0 cases, 9.3, and the 10, 9.8, 9.6. If you see previous simulation, these numbers they are very close to each other. So our just the equation is exactly okay. This is more or less, and when you just put some kind of the thickness plated with the plate with the thickness, and that is reflected, and that just the color and the pixels period become just change. So that becomes just the chirp effect appears. So this experiment and demonstrate this. Our just assumption is right. Okay, next. Yeah, next. And this is an experiment. So when you, okay, so this is a 0.085, just this is a period, okay, of this, the PP. But anyway, OP, you get 0.4.28, and this one is the thickness, okay? You can just say that this is a thickness of this. So when you make it, this is line thickness, okay? One of them is a line thickness. And they have, OP, PP, they have the same period, if you consider, right? So this is a line, the line thickness, 0.085, and this one is, and the space, white space, and this make one period. So they have OP and the PP the same period. So critical, just more or less, when they have the same period, there will not be any fringes. No more or less appears. But actually, if you put it, and the same just the OP disk, the top and the bottom, we are just to put it in. And if you do, and this is just the display your, the monitors and the green colors. And if you simulate okay, with the equation simulators, and you can have this kind of color. And this is, okay, I put some kind of just top plate film, okay, on this, if you see the center, and this kind of colors. So color Moires is also exactly almost the same, actually. Or not, I cannot say exactly, but you can see the almost the same, and the results. Simulation and experiment will be the same. So when you just change your being directions, this will become shifted here, and shifted to the right, and you can see, and this just the part is shifted to this part. And when you see the just the film shifted to the just the left side, and you see it here. So this green moved to here, and this becoming and covers. This become, and from here to covers here. So these cases, and 1.7 GV equal, okay, the being distance 500 and 1000, and they have just experimentally, this is experimental simulation, experimental, they are almost matches. So in this case, we made a T equal 0.68 millimeters. So when they use film, you see how that just the colors, they are matches very well. Anyway, here. Okay, so next. So when you just make actually this one as actually you know, right? They have the same the period cases. Actually, there are no Moires appears, but anyway. So by this thickness effect and by the chart, the colors, and you can have this kind of Moires. Okay, so and this is 0.5 cases, and the 1 meter cases, the 2.0 cases, and well, this case is different, and but they have same period, but they have a different thickness cases, and you can also have this one, and here, and you can have this kind of stuff, but they are almost similar. Okay, next. Yeah, so if you are theoretically, and you can calculate the period. So if you do, and this is exactly the same. They have OP, PP, they have 0.4833 millimeters. They are same, okay, period. But then anyway, the Moires appears, and you can draw and periods by this way. And the center, you can have some kind of just a period, but from the centers, and there is the period become almost infinities. So here we simulated. So just the monitors, you cannot display this one because we simulate 4.5 meters and another side 4.5 meters. This is a nine just meter we assumed. And here by the center, and this is 0, is the center screen we consider just the monitor screen, and you can see you see the Moire period becoming infinity, but only centers coming out. Well, so if you see the 1000 meters is slightly bigger, and the center, but it's still the same. If you go further, and they becoming the period becoming just not defined, that they goes infinity. So this is the same 2 meter cases, slightly just wider, but this part, if you go further, and they become also infinity. The only you can find here, there are just Moire fringes, but here all the infinity, just the fringe period, this part. So you can simulate it this way, okay? So anyway, if you just change your just the image, and you are just being directions, and this becomes shifted here, and you see that here another colors coming out, and this part is the same. And if you go further, their colors become different. So here, well, anyway, I show you those different colors, okay? So simulated with the films, and you can have different colors also. Okay, next. You can generate the different colors. Well, so this kind of pattern too. So this, anyway, I'll just the film result and the simulated result, they are just almost the same matches. This I will show you. And you can change all different colors here. So depend on your just the period and the thickness of this, your line thickness, you can change all differently. And the colors you can generate. Okay, next. Next, yeah. So this is the another examples. And the next, yeah. So this is a rainbow color, and we just display this rainbow color, and we applied anyway Moires. Okay, so there's color Moire here, and you can make rainbow. So you can change, and this pattern completely different. So this is a kind of, you can have some kind of a security, okay, way, and you can change these colors. And this color may be very hard to just copies. This color, just compositions, and this color and the structures, and it be very difficult to, and I consider copy. Okay, next. So now this is another examples, and this is some dynamic, just a visual, okay, effect I want to show. And I display here sky and the blue, and this yellow and the pink color on the monitor screen. So this just photograph not coming out clearly. But anyway, if you do, and if you just put it, the simulators, you can have this kind of, okay, the colors. And if you just with some kind of a film and the period and everything, and you simulate this kind of way, and you see from here, and the center sky, yellow, this is pink, but pink is almost invisible, right? And if you make this, and if you shift your, okay, from this here, and you shift your pink directions, and here, and the yellow, pink, you see, but here, and is almost yellow also disappears. It's possible, so you can make it. So here, also pink is disappear, but it's yellow disappear. So this one, yeah, next. So one just the yellow, this is a 3-1, and this is a, okay, you're just simulation. And if you see here, if you change and just your pink directions, you can have here just only this one. Sky is just up disappear, and next, and here yellow is disappear. Sky appears just very faintly. They appear, and the next pink is remain. But anyway, next you can have pink is gone, and the sky and the yellow appears. So you can have. So you can generate some kind of dynamic effect. So you have just suddenly, so some just colors, just the letters disappear, and some letters appears. So you can make this one, and just the letters smaller, and you can make this color separation just smaller than this one. Okay, period. You can change. So you can have different kind of security purpose. You can hiding some kind of a special, and your just message through this way, right? You can change the hiding also possible. So some kind of encryptions. So when just you do, okay, this line is not this kind of just shape, not a straight line. So this is some kind of sawtooth shape, and you can have, and you see the colors changing the very just strange way. You can change colors. So 500 meters, 100 meters. So this one actually, this is a contrast is not great, but anyway, you can see that way. So you can change all different ways. And through here, well, I don't know what kind of just things you can just expect, just imagine here. But anyway, you can hide the things here. I consider that. Yeah. Okay. Next. Yeah. So this is some kind of the display images, and you display, and this is simulations. And if you just make some kind of film on here, and you can have this kind of color changes. And this is like just holograms, right? So you can just change your directions, and the color slightly change. So here also, and you can see that way. So different color changes. So this is the same as holograms. Yeah. Okay, next. Yeah, next. Yeah, this is so when you just use. Okay, just before that, before this one. Okay, it's difficult. Well, yeah, just well, it's okay, all right. So this is okay, different images you can see with just if you put some kind of just more simulation of the patterns here, and you can have whole different images, and you can change colors a different way. You can modify somehow in here also, and the possible, yeah, and you can just generate some kind of different effect here. Okay, next here. So now, and let's compare So how many different colors by the color Moire and the holograms? Well, you know this when you just the holograms, most important, making color holograms, most important thing you have to choose. So the laser wavelengths. So that just cover this whole shoe and the patterns, and that covers the widest area on this part. So that is just the most colors. This is the most colors we are actually can generate it naturally. So, and if you make the select different laser combinations, and this area is close to, and this horseshoe areas, and you can generate whole kind of color, all natural colors you can generate. But actually, the problem here, the human color discrimination is only 2 to 10 millions only. So this is a natural color, but even this small area, actually all different colors. I don't know how many colors you can expect here. But actually, human color discrimination is only 2 to 10 millions. And well, this is only 2 to 10 millions, all right? So when you use the Moires, we are actually changing colors by this is just the color patterns. So this color pattern, color changes by this is and you change here R and GB, and the color we consider AP just the gray level and the making 255. This the brightness level if you make here and give these images, you can have this kind of colors. And this is a HSV, and the H is a hue, color hue, and this is a color saturation. Color saturation means individual color saturations. And this is a total brightness. And the lightness we call this value, this HSV or HS the L. HSL is lightness, and that's kind of brightness here. So this is a color saturation. So this is only pure colors. You can have these values, and this is the brightness values. So by this way, and this is RGB cases. This is HSV cases, and these cases they have different colors. But these cases, and the R can have 255, G can have 255, B can have 255. But these cases, H can have 360. So this is the S is about 100, and this is 99 something. So this color can be generatable by this model, and the HSB model is just different. And can you get next slide? Yeah. So this is RGB models, and this just we have 256. So 0 to 255. So that just give 256. This just gray levels, and this total color making about 16 or 17 million colors. So this color and more just with just the RGB and the panels, and this just color Moires, the number of color, different colors, and actually maximum these numbers. But if you just this is a level, gray level, you can just the not 8 just the byte, but if you make 10 byte, something like, and just 10 bit, and you can make all different, and these numbers and much more. But anyway, it told, and the human just color discrimination is only just maximum 10 million. You can see that way, and this is too much also for our eyes. So, well, this color Moires and can have all different colors. There is just enough for human, the ability to actually recognize different colors. So it is possible. And the HSL, and here as a hue, color hue, and the saturation, lightness. And here by these cases, and this is just their formula, and they making this way. And this one is about 3.6 million colors. 3.6 million colors only, this one. I guess my consideration about this is actually a reasonable number of colors we can generate, because when you see the color saturation effect and the color, this brightness, this is a total just brightness, and this is a color saturation, the purity of colors. And this one is a gray level, all considering about these numbers. But in any case, so this one is slightly smaller than the human discrimination abilities. But these cases, and much more than the color abilities. So that means, and if you just make it this one, I guess probably match with the human, and the human I told, and about 10 million maximum, but this multiple plus, and divided by 2, just to make about 10 million. So this is what the human can just recognize, discriminate different colors. Okay, next. So this is conclusion. So I just thought, and the hologram and the color Moires, they can have the same. So this hologram is most okay, just we consider diplective optical elements they are. So the diplectical optical element and just color Moires can generate almost the same colors, same just number of colors. They can just only just defined by human, okay, just capabilities, limited by human just recognition capabilities. Okay, so color Moires can made to have similar character OVD by just color shifting, like a hologram saying dynamic visual effect or say encryptions. Well, this one I have to do more study, but actually this is possible. And they change beam and the direction change, and the viewing angle change, and the lightning condition, because the lightning condition is you are illuminating light from the bottom, and they change another just original RGB and there's chirp, and you can have different colors by just illuminating the different just light source. So this is okay. The color Moires also the work can just work as OVDs, same, just almost the same. Okay, principle, the almost same capability. So that's just there are many factors defining color Moire characteristics. So this is all just the factors just making color Moire just you can change that. So there are so many different factors here. So I just did very few. Okay, just line width and colors and the line patterns I used that way. So I don't know just what is actually in there. So I have to do more study, and I need more time to just further get into and find out what is the capability of this one. So the color Moires can do, okay, for the security. But anyway, so from this one, and the color Moires can be used as some kind of security as just purposes, and we can use that one. So this is a color Moire is also making very simple. So as I used to show you, but a very simple way you can make. And this making is much smaller than cost than holograms. So hologram, only difference, hologram have 3-dimensional pictures, but color Moire is no, that the 3D just features it doesn't have. So only that difference. But anyway, and this color Moire have more it's unjust investigated, and the characteristics I consider it has. So that have 2 characteristics, and we have to find out later. So this is all these factors, so many factors, and so this to simulate this one, and we find different characteristic color Moires, and need just much more times to do that way. So this is another just practical. So make it just color Moires, making the more just quick and sooner and the practical applications in just 2 security areas. And the first we need so few microns to nano thickness line drawings. So this is necessary. Because now if you consider is a mobile phone, so you are just the pixel size becoming just 1 micron, less than 1 microns. So now it's mobile phones. So yeah, this is one is required, and another is high refractive index. The most of just the materials you can find is less than just refractive index less than 2.0. So if just transparent plate with refractive is 2.0, and we have just reduced the thickness, so that thickness is invisible. So you can hide it that way. So also another things, just transparent display panel, but this is already we have just the LCD, but LCD is now actually disappearing almost. And this is a OLED, and now LED display is the main directions of this display. So this one actually transparent display already we have. So if you combine this one, I consider, and we can just reduce time of practical applications, and we can just commercialize, I consider, for security area. Okay, that's all. So if you have any questions, please ask me. Thank you. Yeah.
Thank you. Do we have any questions?
Yeah.
Hello, Mikhail Vogorsky, Chernivtsi National University. First of all, I want to mention that very relevant and interesting presentation. Thank you. And just curious, in your opinion, which is more difficult to counterfeit? Traditional OVD, like hologram and structural colors, or this new presented Moire color pattern?
Well, right now I can say, right? So, well, this is a hologram, and right now, and this is the most popular because it has a 3D features. Okay, but anyway, this doesn't have 3D features. And anyway, I just talk with this on our just money printing companies. All right, so they are interesting in that just just the structural colors. Okay, so like the butterfly, but they just they utilize there. But anyway, this one still their considerations. So, but I don't know. So these people have another just view, because this one you need some kind of just a thickness plate you have to get in there. Well, this plate have a thickness. That's why thickness become you have to reduce T. But this one right now, I cannot find that this high the reflective index, this plate, so more than 2. So I can reduce the thickness. But that thickness is also one problem. So right now, this is slightly difficult. But in the future, if I just 3 items I gave the last of my conclusion here, and you can make it possible. And you can make it, and I consider Moires much cheaper and easier to do. I consider that. So this is just, well, maybe another people have another just, opinion, but my opinion is like that. Okay?
Thank you. Thank you.
Is that your answer? Okay. Yeah. So, any other questions?
Good. We're running quite late now, so maybe we should move on.
Oh, already? Oh, I'm sorry. Yeah.
Yes, please. May I ask one question to Professor Son?
Yeah.
Yeah, it's just a simple but practical question. How do you imagine what is the scaling possibilities of this color Moire technology for industrial use? It's simple, or what is the printing cost, standardization, resistance to copying, and so on?
Yeah, well, if you see these holograms on the your credit card, so that is slightly less than 1 centimeter square, right? Only 1 centimeter. So if I thought this is I just make the line thickness the nano 2 micron, and I can make the same size also possible. But the cost is nothing there, only just the color pattern, and we're just the line patterns. So it's much cheaper. You don't need to actually like this one, holograms to making process. It's very easy, and you can do by your just digitally and your just computers. So very easy to do. Yeah.
Yeah. Thanks.
Okay.
Thanks.
Yeah. You're welcome. Yeah. So other questions?
Well, I think we should finish now. So thank you to the speaker again.
Okay. Yeah.
Okay.
Well, thank you very much to inviting me to this conference, and he will just I gave all this disturbance. I'm very sorry about it. Yeah. Thank you. Yeah. Yeah. Bye. Yeah.
Thank you very much.
Thank you.
It was our last participant in this session. Thus, we have a break until 2 p.m. Kyiv time. And at 2 p.m., we start our next session with presentation by Professor Mark Dennis. And the chairman of the next session will be Professor Gbur. Don't forget to change your Zoom links, because every session has its own Zoom link. Thank you. See you at 2 p.m. Thank you.
Thank you.